So good afternoon, everyone, and welcome to our joint webinar presented by Rigaku and Dragonfly. So I see that still the people are joining our webinar. So we will wait maybe 2 minutes more, but maybe I will start with some introductions. So my name is Agnieszka Shalimov, and I'm part of the Marcom team here at Rigaku Europe. So today's session will be focused on computed tomography and some housekeeping notes. So before we get started, today's session will be run for about 60 minutes. We try to keep this this 60 minutes. But please use the Q&A section panel to submit your questions to our presenters. So we will answer those questions after the presentations. And if you have some technical issues, some problems with the connection or audio, so please put this information in the chat, so I will try to solve these problems. We have some videos included in our presentation, so could be that there are some delays or the image will scatter, but it depends on internet connections, but be prepared. The webinar will be recorded, and the recording link will be shared with all the registrants and participants of this webinar. So I think, yeah, we could go further, and yeah. So we are pleased to have two excellent speakers with us today, and it's Dr. Ramil Gainov, a product marketing manager responsible for CT at Rigaku Europe, and Christian Johans, our good partner, senior sales manager in Dragonfly. So welcome. They will introduce themselves in just a moment and guide you through for today's session. So let's get started, and I will now handing over to Ramil and Christian to begin the presentation. And Ramil, the floor is yours. Thank you.
Thank you very much, Aga, for this very kind introduction. Yes, we would be glad today to demonstrate our possibilities, joint possibilities of Rigaku and Dragonfly. My name is Ramil Gainov. I work in computer tomography more than 10 years, and I here at company Rigaku as a product marketing manager. Today, I will be happy to demonstrate our possibilities using a concrete sample, which is as topic as a concrete beton cement. It's a very important topic for many of our users and our customers. Yes. Christian, now is your turn.
Hello, everyone. My name is Christian. I work for Dragonfly. I'm since 13 years in quality assurance with strong focus on metrology. And what this has in common with no matter which application you run using X-ray or computed tomography is that we need reproducible and repeatable data. We want to quantify our data. And with my background, I try to support as good as possible our team with my knowledge, and try to do with Ramil together today an insight into our software solution. And I'm happy to be here. Thank you.
Okay, let's start our presentation. In order to be sure that connection is good, I make out of my video for some time, then I will appear back after presentation. Okay. Rigaku is one of the oldest and rarest companies in the world, covering most areas of application of X-ray technology for scientific research and industrial use. Our company was established in 1951. Today, our company employs more than 2,000 people worldwide. Rigaku has numerous divisions and branches worldwide that are involved in various aspects of its business, the development of X-ray technologies, manufacturing, and distribution. Historically, the first and largest business division is located in Japan and has at least 3 locations. Rigaku develops, among others, powered X-ray diffraction, single X-ray diffraction, X-ray fluorescence spectroscopy, of course, X-ray imaging, or computer tomography. Rigaku CT portfolio includes various computer tomography systems, and this slide shows the main types of commercially available computer tomography. Focus on our CT Lab HX desktop system using a concrete sample. From the registration, we know that many of you do not use CT regular, but are interested in its application. Therefore, the next 3 or 4 slides will be devoted to a simple explanation of the most important aspects. For those of you who already use CT, the next 3 or 4 slides will serve as a brief review. As a first step, the CT operator is supposed to find the right or optimal CT settings to get the best combination of performance, resolution, and scan time. This can be tricky even for experienced CT operators. That's why I'm giving this slide with more details some extra attention. The key point of traditional computer tomography is the penetration of X-ray radiation through the sample being examined. Different components, the material, and phases absorb radiation differently. Some of these components absorb relatively large amounts, such as iron, others absorb significantly less, such as carbon. The radiation passing through the sample in 3D mode can therefore be used to display the structure of the sample in accordance with the 3D distribution of the sample components. The size of the sample component is also a key factor, as a larger component absorbs more radiation than a small component, even though these components are identical. Consequently, relatively small samples are always better suited for X-ray penetration than relatively large ones. In other words, if the sample is too large or too dense for X-ray computer tomography scanner, the power of the X-ray system's X-ray tube will be not sufficient for X-ray radiation to pass through the sample or absorb anything. In this case, the CT operator is supposed to find a balance between the size of the sample and its absorbing properties on the one hand, and the power of X-ray computer tomography scanner on the other. Another key factor is a magnification factor, which allows you to obtain the highest possible resolution, enabling the CT operator to resolve the smallest possible components of the sample. The diagram on the right side illustrates this situation. I won't go into complicated explanations of the magnification factor here, because each of you uses a camera on your smartphone. Just imagine that you are trying to photograph an object that is far away from you. In this case, you will only be able to see the main and relatively large details of the object. If the object is very close to you, you will be able to see even the smaller details. A similar concept is used in traditional computer tomography. If you are placing the small sample for CT measurement, you can place the sample closer to its X-ray source to improve the resolution. A large sample, on the other hand, will be placed far from the X-ray source. In this case, the resolution will be somewhat worse. In the case of desktop system, the X-ray source is fixed in one stable position. Sample is fixed between X-ray source and detector and rotated 360 degrees. In this case, we receive so-called two-dimensional transmission patterns, which allows to see the structure of sample. But with two-dimensional transmission picture is not 3D reconstruction of the sample. It's only transmission, which allows to see the general structure in one direction. Then we use our Rigaku software in order to collect all these two-dimensional pictures into regime, in order to collect all these images. And after this, our CT Rigaku software makes a 3D reconstruction, complete 3D reconstruction, as you see on the right side. The step number 4 is a 3D CT analysis, because as we have talked already today in the beginning, sometimes you need not only the 3D reconstruction of the sample, but you want to observe 3D analysis, like porosity analysis, volume distribution, but maybe not only porosity analysis, but inclusion analysis or different phase or aggregate analysis. Let me explain some details of our desktop computed tomography system, CT Lab HX-100 and 130. Our CT Lab HX system benchtop has two modifications. One of them provides the voxel resolution down to 1.3 microns, another one down to 2.1 microns. The maximum voltage is 130 kV. The fastest scan is possible even with 18 seconds of measurement. In the case of desktop system, X-ray source is fixed in one stable position, while the detector can be moved closer to the X-ray source or back to the opposite direction. This results in a change in the distance between the source and the detector, as well as the distance between the source and the object. These options allow you to find the optimal sample position to improve performance and resolution. The sample is placed on a stage that can be moved between the source and the detector, as well as in a perpendicular direction. This stage can be moved along the vertical axis, which allows to measure different parts of the sample at different heights. These three-dimensional measurements can be then combined into a single 3D file using the stitching function. If the sample is relatively large compared to the detector area, it can be still measured using our offset scanning mode. In addition, the desktop system can be equipped with various accessories for many special automatic sample changer, which allows several samples to be measured in a single cycle. This option is relatively popular among scientists and industrial reference laboratories that examine various types of concrete samples in mini series. I focus on a practical example of investigating concrete sample using CT principle and the Rigaku desktop system outlined above. This slide shows a concrete sample looks in the CT cabinet of the desktop system after installation and before measurement. We have prepared a short video record for you that demonstrates the installation process in the next slide. You can see all the key components that can be used to install a concrete sample. From the left to right, we see a high-precision stage, a gray standard plastic cylindrical sample holder, which can be installed very easy on the sample stage, and then we can put our concrete sample. Formally, it's already okay. But I will recommend to use 3D printed sample holder, which is red in this case. This 3D printed sample holder is installed in the same way as the standard sample holder. In some cases, it's also necessary to install an extension that allows the sample to be fixed at different height. Samples or different concrete samples can have relatively different shapes, and therefore the 3D printed sample holder can be a very good option to stabilize the sample during the measurement process. Now we can observe how we install all this construction inside of our CT cabinet. On the left side, we see X-ray tube. In the center, we observe motion system. And on the right side, we observe detector. Now we install our construction. Now we use our ring for tight connection, and that's it. Then we close the door of our X-ray system, and mechanically our sample is ready for measurement. But before the start of measurement, we need to be sure that sample is located in the center of our detector. So we make a rotation 360 degrees in order to observe that sample is really in the center of measurement area. After mounting the sample as described in the first slides, it is necessary to determine the CT settings for further 3D investigation. The Rigaku software panel, marked in red, allows you to vary many parameters to find the optimal CT settings. This slide shows with control panel for the measurement equipment with more detailed information. Here you can easily change the parameters. This includes changing the voltage, current, and focal spot size of the X-ray source, mechanical filter, for example, aluminum or copper, moving the sample relatively to the X-ray source and detector, correcting the field of view, detector properties, for example, pixel size in the form of binning, the number of two-dimensional transmission projections, the number of iterations, and many other settings. Concrete samples can be widely changed so CT settings may differ from one to another. For example, for a concrete sample, after several preliminary short test measurements, I have found that a voltage of about 110-130 kV and current of about 120-150 microampere with aluminum filter provide relatively good contrast as shown in the previous slides. If you have many samples or one sample that has been measured several times, you can easily use the database software panel. The database software panel allows the CT operator to find all the necessary CT settings from different measurements, compare them with each other, and open the reconstruction data for other reconstruction iterations if necessary. After inspection of the sample, a new window will automatically appear, signaling the successful completion of the measurement process. The Rigaku software panel, marked in red, shows this window in the case of our measured concrete sample. This window allows you to make further selections for 3D reconstruction settings. For example, there are various mathematical algorithms for 3D reconstruction, allowing the CT operator to find the optimal one for their specific sample. The CT operator can apply all these algorithms and compare them for further analysis. Example for beam hardening correction, which is very important for many applications, including dense concrete samples. This effect occurs because X-rays are polychromatic, and different energies of X-ray source are absorbed differently by the components of the sample. To compensate these effects, the Rigaku software package implements tools for easy application of beam hardening correction by entering correction values. The CT operator can use different values for beam hardening correction and then compare different 3D reconstructions to determine which is the best for their specific application. There are many other options such as additional mathematical denoising of CT images or ring artifact correction, which can be applied in a similar way to beam correction. In the case of our specific sample, I did not use beam hardening correction due to the use of aluminum filter, but I did use a ring artifact correction and noise reduction options. After selection of settings of 3D reconstruction and running of the process, a new window will automatically appear, signaling the successful completion of this process. The Rigaku software panel shows the 3D reconstruction of our concrete sample. The first window displays the basic CT settings that were applied for this measurement, while the other three windows display three projections, XZ, XI, and IZ, on the corresponding virtual two-dimensional slices of the concrete sample. The Rigaku software panel on the left displays a variety of icons that reflect various options such as zooming or rotating CT images, changing the gray value to improve the visualization, changing virtual slices, and many other options for post-processing. In our specific case, with the concrete sample, we can observe the sample itself and 3D printed sample holder, which does not obstruct the view of the sample. Next slide demonstrates our sample with a zoom, and we can observe beton sample itself. It's a gray color, but we can observe also different white phases, sands, different aggregates, which demonstrate multi-component character of this sample. And of course, we observe different pores and bubbles, which reflects that this sample has a lot of air inside as well. It's another slide which demonstrates our sample with a good quality, everything is clean, and image is sharp. After the measurement of our concrete sample, we can open special folders which are corresponding to the measurement process, and we can open special Vox file. It's our Rigaku format for 3D reconstruction files. And of course, every CT user can open also raw data, two-dimensional transformation pictures or images in order to make his own 3D reconstruction if he or she wants. I think this measurement process was done, and now we can give the words to my partner, to my colleague, Christian, for further demonstration.
Hi, everyone, again. I'm going to share my screen now to dive into the topic of Dragonfly. Just give me a second. Okay, here we go. So yeah, welcome again. And I would like to give you, first of all, a short overview of what Dragonfly is. So as Ramil already presented very well, it's the hardware side of creating CT data or X-ray data. And on the back end, we have the thing, what we have to do afterwards. We have to maybe quantify data, get some analysis, segment it, visualize it, whatever you want to do. And we have an advanced software solution for that called Dragonfly. We are a company based in Montreal with 35 developers creating Dragonfly, and we belong to the Comet Group based in Switzerland. So how we see, we support our innovators in science and industry, and we develop a 3D visualization and segmentation software. So you can start with 2D images from a microscopy, over CT images in one time, or 4D when you have kind of multiple time lapses. This software helps you coming to your goal. And I think in most of the cases, when you have the data created, you want to work with those data and get something out of it. And for this, you choose Dragonfly. So what Dragonfly is famous for is, on the one hand, we do really nice visualization of your results. You're going to see that in a practical example later on. We have state-of-the-art deep learning. I mean, the more famous word is maybe AI, artificial intelligence, but deep learning algorithms are making your life more easy when it comes to segment data. We have a wide range of segmentation tools. And for the ones who are into scripting, we have Python automated tools, which is really nice because you can explore the software on your own without the software telling you what to do. And we have, we're excellent in image analysis as well. So by standard, we diversify our applications in two segments. So on the one hand, we have research and science, which we split in life, food, material, geosciences, and museum collections. And on the other hand, what we do in the industry is the analysis of semiconductors and electronics, energy storage like overhang analysis and batteries, additive manufacturing, metal casting, and plastic injection. So this is concerning the segments. And I believe strongly in seeing is believing. That's why I don't want to dive into different features. I have a few examples with you. And one highlight comes from Ramil, but I keep it for the end, so stay with me. So one is the crack analysis. I really like this example and this visualization you see here just for the explanation. So the image on the left-hand side shows you 50% of the concrete itself, or of the rock itself, from a drill core. And on the right-hand side, this colorful mapping here is the thickness of the crack inside your rock. So this is doable. And so why is Dragonfly ideal for this scenario? We have a voxel-based analysis, so it makes the inspection fast, intuitive for users, and you can measure the thicknesses, the volume, or the surface area with or without meshing. Then we have a high accuracy due to subvoxel thickness algorithms. If you are, and Ramil described it already very well, familiar with CT, there are some limits, especially the larger your part, by generally, the larger your voxel size. Voxel is a 3D pixel. And this makes it sometimes quite tricky if you want to get the information of the tiniest structures, but you have a large sample, you are limited to the voxels. And for that, we have algorithms to get as closer to the real value as possible. We have intuitive visualization. You see that later on. It's simple. We use simple presets to make it as comfortable as possible, especially for starters. And so just in the second layer, it gets maybe sometimes complex depending on what you want to do. But for the introduction of the system, the goal is to give you the possibility of a quick quantification of data and its visualization. We have integrated statistics and reporting. So of course you can kind of run a batch processing, for example, and export this quantitative data as a CSV file, text file, the histograms, or the colorized image to your inspection folder, for example. And flexible workflows. So we start with classical thresholding processes. We use OTSO in this case, up to AI-based segmentation. And what this means, we're going to see later on. And there's one highlight is that we have a plug analysis add-in for the software available. And I just want to mention that here. So this is specifically for the purpose for analyzing plugs like you see on the right-hand side. And if you're interested in that, get back to Ramil or myself. We're more than happy to answer your questions. The second application is called the cellpose segment anything. Segment anything, where does this name come from? It is because our deep learning library is coming from Meta. Before we used Google, now it's Meta, and it comes with the idea that you can segment everything you want in your image without any pre-training or something like that. A really cool tool. And the people from Cellpose created a tool that's made for like cell-based structures, but you can use it for powders as well. And here we see how it works. So this is like a sand tube, a tube full of sand. And what it does, it's a one-click solution to do immediately the quantification of your corns within a 2D image. This is already really intuitive, treated in Dragonfly, but as a second step, we are speaking about CT today, so we have it for 3D as well. It's the same approach, it's a simple click, and then it does the segmentation combined layer by layer of each corn or each rock piece you see here. And what else you see is a so-called pore network model. So you can run the calculation of your pore network model. You can run a tortuosity analysis. All this comes with this software tool, and especially the new feature helping to get quicker to your successful result. So one last thing before we switch to Dragonfly is join the community. I invite everybody, no matter if you're a scientist in the industry, in a research lab, or wherever you are, we have Dragonfly Social. It's the possibility for you to get sample data, to play with the software, download maybe a trial to test the software on your own. You're more than welcome to join us. And if everybody made a picture now of the QR code and already joined the community, I will switch over to the main software, which is Dragonfly, right? I do it like that. Then you should be able to see it. Okay, so this is the interface of Dragonfly. And if you are familiar with 3D inspection software, design software, reverse engineering software, it's basically nearly the same, at least in the first look, because we have a 3D window, we have 3 2D windows for the CT analysis, and then in the left-hand side, we have the basic operation and segmentation of the software, and on the right-hand side, we have the possibility to play with the different analysis segments we integrate here, like the CT image, the region of interest we create, and so ever whatsoever. We start directly opening a file because, as I said, I mean, we can look at the empty window and I can explain you the features, or we see directly what I mean with that. So Ramil sent me a .vox file, which is the standard file coming from the Rigaku systems, and I choose that file. You see it here, the .vox file, and now it gets integrated in this interface. And I can basically, because all the informations are already in the metadata of the file, I can directly open it. But I like it. I like to have my data easy. I crop the data a little bit because I just want to inspect the cube you already saw in the Rigaku video, and not everything like the support or something around. This has the benefit that it reduces my inspection data as well, and I can present it to you a bit faster. Okay, so we have immediately, as I said, the 3D volume here. You see it a bit dark here. That's on purpose because I want to keep some surprise for the end. And we have the 3 windows here. So I can play with we have 65,000 gray values because each voxel gets interpreted or signed with a gray value. And based on the window leveling I'm doing here, I can enlight some gray values and make it a bit more visible. I think that's everything for now. If you're interested in this technology, you can dive into this topic later on. And yeah, so what we have with this, I have to put my window here a little bit aside. I increase this window now. So this is one cut through the part. And we see it in large and in all the 3 layers, in X, Y, and Z. Normally, if we do an analysis, we align our part. So this is what I'm going to do now. I click in each window and align a bit the part so it's orthogonal to my coordinate system. And this makes the approach just a little bit faster. When this is done, I open it, and here I have the possibility, for example, to scroll through my part and see all the areas that might be interesting. For now, I would like to dive deeper into analyzing the pores and inclusion in here. But of course, there are different materials. We see very shiny materials. So very shiny material in this case means it is quite dense, because you see on the outside, there's typically air. Air is very black. So it's easy to penetrate. And everything in between can be like a different stony material or a pore, whatever is in there. So this is a perfect example for multi-materials and its inspection. So this is what it does. And as I said, we are famous for segmentation. And Dragonfly allows you multiple ways of reaching this segmentation, especially in the beginning. If you want to have fast results, we have this solution for you. It's a one-click pore segmentation solution. And I'm going to present this to you. When you right-click on the CT dataset, which you see here, then we have one option. It's saying automated porosity segmentation. And I choose the first one. It's single material basic OTSU. That's kind of when you open the data set and you click on that, you get an immediate indication is in which direction are we going here. So all the pores are detected except the ones connected to the outside air. And you can quantify this data immediately because we have now our multi-ROI with the exterior, which is the air outside. I can delete that because I don't need it for quantification. We have the matrix. In this case, it's the main material, including all the very shiny, dense parts. And we can delete that as well because we are interested in our pores. And for that, I can run now a measurement on this. So I create a model. It's called a multi-ROI. And this multi-ROI does the following. It already separates my general voxels, what I could use to calculate a percentage coming from the main volume. I could use it now to quantify each of these pores you see here. And this is pretty nice and simple made because I can just click on measurements and then I can choose the measurements I want to do. So we are in 3D volume, so that's why we take the volume as the quantification, for example, and it's immediately calculated. And when I select volume, I have already the quantification of that. I go in the other direction because we have kind of larger ones here, and you have all those results. You can export it now, or you can visualize it. And visualizing it is like the next topic. So we have our 3D volume here. And I'm sometimes, I don't want to say I'm lazy, but I really like the opportunity to have presets for 3D rendering. And those presets allow you to not look too deep on the single screws you can turn to have a nice image. You have here the possibility to immediately get a nice 3D rendering of your part. Here it comes with nice shadowing or and the gray values are adapted to it. And now you can play with it. You can increase the quality and whatsoever. But I think this is already a very nice outside of the part. But we have CT, so we want to take a look inside. And we already quantified our data. So if you want to have like a fast, very representative presentation of this, we can use something called the splitter. It's a new functionality in here. And the splitter allows us to clip the part in half. And if we activate now on our quantification, we are immediately there. If it's loading right. Okay, here we are. So we have immediately the quantification and we can see there are a lot of pores inside. So this is definitely something we should get rid of because we can't take a look on every pore we kind of lose then the overview. So what I can do is now I have something called the measurement inspector and it opens up in parallel to that. So what does the measurement inspector do? If it's loaded, I can reduce the ones that are maybe not interesting too much. And I can then say, please take the ones that are a little bit too much and decrease the visualization of it. So what stays is some visualization. Let's take the opacity away as well. Yeah, like that. And now what you see is the 3D visualization of the part. And you can now export those data and play with it. The separator also allows you to move the splitter around to give you the possibility of getting better insights. And that's basically it. That's what we can do with it and to quantify the data. Unfortunately, it looks like during the Zoom call, my 3D rendering is a bit suffering, but I think you understand what I mean showing you this. So this is basically, let me deactivate this. So this is basically it. I delete the splitter and then you can see the full point cloud. And this is the volume you can see. Okay, so this is it concerning the part itself and the possibility of taking a look at the data. If there are any questions, you can put them in the chat and I'm more than happy to answer them later on. Now we want to use the last 11 minutes. I'm going to be quick. I hope not too quick. We're going to take a look at another sample made of monomaterial, because in the Rigaku sample, the rock sample, we have multi-material, and multi-material means training deep learning for training a deep learning, you have to add some classes, which takes a bit more time than we have in this session here. So for example, I take another example in this case, which is a bit simplified, but makes it very understandable what Dragonfly in this case does here. So we take a metal cube. It's famous in additive manufacturing. If you have a 3D printed cube, you do like a test cube to figure out the quality of the printing process, and it gets immediately imported. So this is the 3D printed cube, and this is what it looks inside. As I said, it looks a little bit different than the rock sample you saw before because it's a monomaterial mainly. There are some powders which are quite dense, but it works perfect for an introduction to what is deep learning. So you saw before, we have an easy introduction to detect the pores, but deep learning is helping you to have a more advanced insight into your part, because as Ramil already said, CT scans come with so-called artifacts that might come due to dense material, which creates like artifacts that look very shiny in the image. You have maybe a stitching process, something that is kind of irritating the image a little bit. And in this moment, when you have irritated images, maybe the thresholding process, like I presented to you, is not advanced enough. And for that, we start using the deep learning model to have a more maybe automated version of segmenting something or a better way of segmenting something. So for that, I take this cube and I start my segmentation wizard. So the segmentation wizard is the possibility to do this training of a deep learning model independent from the software itself. And for that, it is quite simple made because we just integrate a frame which we use for training the model. And you can see the deep learning of a model, of the training of your deep learning model as a child, and you have to teach this child the differences between the apple and a banana. So in this case, it's the same thing. Your deep learning model doesn't know anything. So, and that's why we have to tell the model what is the situation here. So we need three classes. One is the air, the other one is the material, and the third one, I can add this class easily, is the pore, for example, or the pores. So I have basically with this everything inside I need to define. And don't worry, I just use a small frame because it's faster showing you the teaching. So what I do now, I want to detect the outside air. So for that, I have a thresholding process, for example. I have multiple ways doing it, but this is one way of doing it. So I can use the outer range, so the more darker gray values, and add it to my class. And then I use the dense ones to define my material. That's a good first step. But then I have my pores, and they are already detected as air, which is legitimate because the air inside looks similar than the air outside. So for that, I have a very easy tool. And this is where Dragonfly came up with in, I think, 2017, 2018. So we have the possibility now to detect those pores very simple with like paint, to be honest. You just paint those areas, and don't worry, you don't need to do it every time. This is called teaching a deep learning model. So it doesn't mean applying by hand every layer by layer what was usable, what was the normal case like years ago. Now we have the modern approach. We can train our model. We do it 1, 2, 3 times, and then we have kind of our work done. So this is the mask I filled. And now what I want to do before I start training my deep learning model, I need another area to monitor my results, because I want to show you immediately what Dragonfly does when it starts its teaching of the deep learning model. And for that, I call this whole stuff monitoring. I start training, and then it already loads everything into the training of the deep learning model. And this is what you're going to see now. So this is the mask, and it starts freaking out immediately. So it's like, what do I have here? And the goal is it runs epochs. I applied 100 epochs, but we don't need it today. But these epochs in this epochs, we train our model based on the input we gave. And as you saw, we have like a whole cube. We cut it one slice of a cube and defined one frame to teach it. And then we said, okay, that's what we have. And now train another frame on that. And what we can immediately see, it does work directly. So that's sure, it's a simple sample, but it's a realistic sample. Don't get me wrong, this is a realistic application, but it's nice for the explaining this. So I can stop here. It automatically takes the best result it had from this training and applies it immediately to the one I used to train it. And that's basically it. So now I can transfer my data to the training image, and I can say, okay, this is the one, it's trained, and now I can increase the size of this again, and maybe I choose another one last one to check if now my training is complete. So I call this monitoring again, because that's the one what we want to see in the training of the model. So it starts the training again. And yes, we are using a small data set. Does deep learning mean you have very fast results like I present to you here? No. If you have very large data sets, this process takes longer. But the good thing is, if you have repeatable parts or a very complex part, then this is the tool you need, because you train it once and then it works every time again on your hundreds of parts, especially for drill cores or plugs. You analyze, maybe you have repetitive plugs, so you train your model and then you have it every time. And that's kind of the thing. What we did here, we trained our own deep learning model that we can apply to our part now. And I did it fast, and we can see now what the result is. So there might be some bits and bytes shifted to other classes to have it a bit more robust, but it's already a start. And I think this is the most important thing for today, to give you like a quick insight into this. So this worked pretty fine. I push it upwards and call this one now mixed again, and now I can leave. And what I have to do is I publish. I publish my model, and now it's integrated in my library. I have a deep learning library where there are already some presets, all my own trained models. And when I go now in the segment window, I have segment with AI, and then I can choose my Rigaku pore analysis and, for example, apply it to my 2D image just for testing, because in 3D it takes a bit longer. So this is what it does. It automatically, and it's very similar. The thing is, it looks different, but the application itself is the same than the one-click solution we used. It just applies a better model because it's aligned to your data set. And this makes it very robust. And yeah, you can see we have our air. We can get rid of the air. We have our material. We can get rid of the material. And what do we see? There are some pores left. Of course, I didn't teach the child in detail the differences between an apple and a banana. And the thing is, the data here are very noisy. And very noisy is kind of the thing that makes it sometimes a bit tricky to identify a pore and to be sure this is a pore and this is not a pore. But nevertheless, this is the training of the model. And if I apply it now to the full data set, I have it. And what do I mean with things like, is this a pore? That's kind of the question. I think it is. But if I go now to the next slice, it's gone. So that's the question. Normally, you say you need 2 by 2 by 2 voxels or 3 by 3 by 3 voxels to identify a pore. So, and in this case, I think I did quite a well job with my training of the model, because this appears only in one slice. So That's the argumentation behind this. And right, that's basically it. That's the insight into Dragonfly on those examples. We have quite some time left for questions and answers. And I hand over to Aga or Ramil, whoever wants. And yeah, thank you.
Thank you so much, Christian. Yeah, it was a really nice presentation for both of you. Thank you. So yeah, we have some question. Actually, I think it's mostly related to you, Christian. So Francisco is asking, can you show how to calculate tortuosity?
Okay. So in this case, it's I don't have a sample in mind now where I can do it that simple, because the data sizes are quite large, and it would take some steps which would kind of push out of the webinar. But I would be more than happy to get in contact with Ramil or me, and we do it on your part, or however you want to have it, because I would like to use the chance to give you an insight on that.
So Francisco, we will stay in touch with you. So the next question is from Julia. Does Dragonfly get the size of the image sample from the data set, or do you have to manually input the lengths?
Okay. So the good thing is, if the data come from Rigaku, we have the box file, and in the metadata, there's the voxel size already integrated. And if you have millions of voxels and you have this one specified voxel size, it is already in the right scale. I know maybe where this question could come from. In some cases, when there's no metadata and you don't have the voxel size, you need to get your scale from somewhere. It is just without the metadata, and especially voxel size or a scale, your file is blind and you have to manually input what a voxel size is. It might come in 2D. For example, if you take microscopy data, it can come to a point that you have like your 2D image and you have a light scale on there. We have a calibration process for that, which is quite nice, because you just do an A to B measurement and then apply it to the scale of the image, and then you have it done. But I think in this case, sorry, Ramil, I can answer this question from Rigaku side. The voxel data are already implemented in the .vox file.
Yes, just at some point, yes, we have a cooperation between Rigaku and Dragonfly. And if you use Rigaku CT systems, then Rigaku Vox files can be immediately opened by Dragonfly without any additional preparation of files.
So there is one more question from Serene. It's pretty long regarding the version of the software. So I'm not sure if you want to like answer, or maybe directly to Serene answer about like the versions of the software.
I understand. Yes, I understand the question. It's available in there. It would be great if you could test the new 2025 version on your own. That would be perfect, because it opens you up much more possibilities.
Yeah, so I think, yes, that's it. But to our audience, if you have any questions, so feel free to contact Ramil or Christian, and yeah, they will be more happy than to answer your questions, maybe after you will have some more. And also feel free to contact us if you want to have some demos on our instrument in our lab. We have CT Lab HX, so feel free if you have some samples and it's your first time with the computed tomography. We are happy to help you and give you some insights in our lab based like in Neusenburg in Germany, and yeah, even like together with Dragonfly.
Yeah.
So
there are two more questions.
Yes.
Aga, is it okay if I answer them?
Yes, sure, of course.
Okay.
jump in.
So converting, I love that question, because in 2024, the version before the actual version now, we had already surface determination, but it was voxel based. That's kind of not state of the art anymore. And we integrated in 2025 subvoxel surface determination. So it helps you getting all the details and you can export it as an STL. So yeah, no matter if you do metrology purposes, which some of them are covered in Dragonfly, but if you want to have more advanced metrologic solutions, then you can put it on your design, reverse engineering simulation software as you want. And the other question is the microstructure analysis of bones. I give a clear yes. There is a bone add-in, and there is the possibility to do it with a normal version of Dragonfly as well. Get it online, download it, and if you need help, get in contact with Ramil or myself.
Yes, I just add that bones are also possible to measure using our desktop system. We have already did a lot of bones measurements with Rigaku. And of course, just emphasize Dragonfly. Christian, please correct me if I'm not right, but as far as I know, again, Dragonfly has special also module only for bone analysis. So maybe we can think about next webinar about bone analysis with Rigaku and Dragonfly.
Oh yeah, definitely.
So I think like we could close our sessions for today. Thank you very much once again for participating, and yeah, we will set soon like the next webinar, probably next year, and yeah, stay tuned. Thank
Have
you
a good
again.
day, everybody.
Thank you.
Bye.
Thank you.
Bye.
Bye.